Hi and welcome to today's webinar with the topic Cost Reduction in Serial Production with Spike. I'm very happy to welcome you as such a big audience today. And front up, I'd like to recap what we've already shown in earlier webinars. So for those of you who joined earlier webinars, they might be aware of what I'm going to show you next. For those of you who are new to our webinars, will be a short introduction into the capabilities of Spike. So what we can see here is a status quo in milling operation as we know it from today's times. We manufacture a few parts, and after we machined all of these parts, we can see with increasing wear of our tool, our workpiece quality reduces. Or in the worst case scenario, if one of our cutting edges breaks, we'll completely lose our surface quality of the tool and we have more rejected parts produced. Problem by now is we can detect this problem after the process, in the worst case after a whole series of products we manufactured, so we'll produce many parts for the litter. Now this is where Spike comes to act. With the Spike Polar we are now able to detect the quality of our tool or the status of our tool within the process, and so we are able to rematch the status of the tool to the workpiece quality. So as you can see on the top here we have a new tool and we have a quite small Spike Polar with equal forces for every single cutting edge. With increase of tool wear we see that the forces increase likewise, and also they are not equally distributed anymore. Now, if one cutting edge breaks, we don't have any forces from this side of the tool, and we completely lose the surface quality, which we are able to see in the Spike Polar. Now, for us as person, this is quite easy to see and to interpret what will happen here. For the machine, it's not possible to react on just the Spike Polar. And this is why we develop Spike KPIs. These are patterns that enables the machine to sort of read the Spike Polar. So we are now able to say with a new tool, we have like even distribution of the cutting forces. So we have asymmetry, we have a minimum tool load. With increasing wear of the tool, we are now able, by the area of the whole Spike Polar, to determine, all right, we have an increased tool load, so we could now give a warning signal to machine operator and say, look, your tool wear increases, look at your tool if it's still okay, and if one cutting edge breaks, we lose the symmetry of the Spike Polar. With our algorithms, we are able to tell the machine, now you lost the symmetry, so one cutting edge broke, stop the machine, change the tool to a sister tool, something like this. Now, how would this exactly look like in machining operation? We have, again, a new cutting edge. In the process, we can see directly the Spike Polar, and also just in time, we are able to analyze our Spike KPIs. Now, if we insert a tool with a worn cutting edge, again, during operation, we see the Spike Polar, and also during operation live, we are able to calculate our Spike KPIs. In this case, we don't have a connection or a command enabled to the machine, so we are just running the tests. But you can imagine, like in this case with the broken cutting edge, we will now be able to send a command to the machine to stop the machine or to change the tool to another tool, so that we don't lose our surface quality. Another common problem will be in the drilling operations. We have 20 drill holes in this case, and on the top we can see the axial forces in blue, mainly due to the feed force of the drill, and also the torsion forces in red. There are no variations within these 20 drill holes regarding axial forces and torsion. Now, if we have a closer look at the bending moment, we straight away see that there are some errors in the bending moment. So we have increased bending moments with some drills. If we have a closer look at the outlet side of the drill holes, we can see that some of these drill holes are deflected compared to the others. So we had a run of the tool during operation, but again, we only are able to detect it afterwards, unless we use our spike system, where we can see in process the increase of bending moment, or also on the spike polar, where we straight away can spot these mistakes. So with a good process, like in this case the fourth drill hole, we are able to just see a small dot with the spike polar. As the bending moment increases, also the spike polar widens up, and in the extreme case of drill hole 16, we get a complete circle, and so we can tell the machine again, wait, there was a mistake with your drill hole, and so there's no need to check the part afterwards, because we already did some sort of quality check within production. So again, let's have a closer look how it could look like. So what we've seen here are two drill holes with a centering, and the center was made perfectly in the same position as the drill hole itself. We can see here small forces and bending moment, and also a spike polar, which is very small and in the center. Now the second two drill holes are produced without any centering. And again, we can see small forces and a good spike polar. Now with the third and with the fifth and sixth drill hole, you can see that we had an increase in the bending moment, and also got some sort of circle in the bending moment, which is visual in the spike polar. In this case, we milled with a offset centering, so we had 100th mil offset between the pre-drill operation and the drill operation itself. Now for the last two drill holes, the machine table was inclined by 2 degrees, and again, you can see the very high bending moment and the circle in the spike polar. So as said before, we are now able to monitor and detect these problems within the process, and to avoid the need of afterwards quality checks, since we already know what happened during the process. So I might just shortly introduce myself. My name is Matthias Pfuhl. I'm responsible for the southwestern area of Germany and sort of substitute Leonard Riele today, who's on vacation this week. So you might not have heard of me before, but you might be aware of Leonard Riele. But if there are any questions or requests afterwards, feel free to contact me or Leonard as well. I'll forward your requests if needed, so feel free to ask. All right then, let's move on to the agenda of today's webinar. So first, what are the challenges in machining? What are the cost drivers in serial production? And how does a amortization generally looks like, or what are perspectives of a general amortization? Then a few applications where spike could be used or is already used in serial production. And last, I'd like to show you the complete solution, the key benefits, process and identification. After this, we'll go through a concrete or specific use case based on hard turning operation. So we'll show you 4 steps to the cost saving potential with process identification, process analysis, long-term diagnosis, and the implementation of the system. Then I'll show you some savings potential, and finally there will be room for feedback and outlook and also your questions. So as said, there are places for questions in between. We'll have a place for questions between the introduction and the use case, and also at the end of the webinar. And if there are already some questions, now's the time to ask. All right, since there are no questions so far, I'll move straight on to the challenges in machining. So what are the challenges we all day come up with? Reduce quality costs. We have quality inspections, as said, after we produced the parts. So we have non-value added operations. And the problem with these non-value added operations is they cost us money but we can't charge this money to anybody else. So we need to reduce quality costs to a minimum. Another thing we often see is the frequency of setups. So we need to reduce the frequency of how often we can set up or must set up a new system. So challenge is to optimize the toolware so we don't have to set up this often. Again, non-value added time. Common problem, errors in production. Again, we need to minimize failure costs and prevent errors so we don't have error prevention costs. Again, non-value added costs need to be reduced. Now, since we reduced the non-value added cost, if we were able to challenge all the first three things, we are now able to increase the production volume because we have more time left to spend with producing parts. So increased production volume is also a common thing. And finally, of course, make optimal use of tool lifetime or optimize cycle times of our processes. Now we need to ask a few questions first. So what problems in which applications cause high costs? Can these problems be monitored? Which of these problems are low-hanging fruits, so easy to monitor, but with a very high return on invest? And also, how much savings potential does monitoring this process offer? So comes together with question number 3. How much can I save if I monitor these processes? Well, let's say most common cost drivers in machining are, of course, material costs, personnel costs or quality-related costs, tool costs make also up a small amount, and of course, machine costs. Now, what causes these problems? Machine. We have the machine hour rate, the number of machine downtime costs, how often we have to change our tool, or as said, non-value added operations that must be done on our machine. These will lead to higher machine costs. Now, component, material parts. Process time per part. How long does this one single part needs to be machined? The number of produced parts per year. Can I split my costs to a quite large amount of parts, or do we only have a small amount of parts where our costs needs to be distributed? Rejects due to tool breakage. Again, how much failure parts do I produce? How much costs do I cause due to tool breakage? And the employee, again, costs without value adding. So is the machine operator required to do quality checks at the machine, which avoids him from producing other parts? And again, the production time per year. The tool, of course, how many parts can I manufacture with one single tool, so the tool life, the cost per tool, and how often does my tool break? And finally, what we've seen at the beginning, the quality. Reduction through spot checks, downtime due to spot checks or test failures. Our pro-micron's philosophy is your invest in the Spike system needs to amortize within 18 months. So we set ourselves the challenge, if we are not able to reduce your costs for machine, components, tool, quality, whatsoever, this much that you are able to amortize your invest within 18 months, we are not quite willing to go on the next steps with you, because that's our philosophy. Within 18 months, you need to benefit from our system. Now, where can you use Spike in serial production, or where is it already in use? Of course, we have the common operations of milling, drilling, threading, but also grinding, turning, and FSW are thinkable of. And in the drilling, threading, turning operations, there are already systems on the market or we are in close contact, as well as for milling, of course, where customers ask us to monitor their processes. Which customers are these? For example, like Airbus, BMW, Grob, ZF, whatsoever. So lots of big names in the industry. Now, how does the Spike solution look like? We have here at the right-hand side one example of a machine park where we set up our Spike systems for 24/7 in monitoring in serial production. There are different ways what or how to monitor. You can think of tool monitoring, force-based dynamic tool change, monitor the cutting edge breakout of the tool. You can think of quality control inline as seen at the beginning, monitor surface quality or monitor shape and position tolerances, and of course process monitoring itself, so negative event monitoring or monitoring of process stability. It all depends on your demands. But we deliver you a complete solution that perfectly fits to your demand. So either with the Spike Mobile as a retrofit solution which can be integrated into your existing machinery, or also with the Spike In spindle, which is by now exclusive with our partners DMG and Grow, we will deliver a complete solution that covers your needs for cost saving in the 24/7 series production. We've already heard it before, but I just want to quickly recap the key goal and key benefits of Spike Easy Inline. So as said, we have the process monitoring, so monitoring of tool breakage, chip clamping, detection of workpiece positioning errors, the single cutting edge wear monitoring, inline quality control, adaptive feed rate, such things that are directly related to our process. Or we have machine and spindle protection, so quick stop during collisions, predictive maintenance, or spindle and axis status monitoring to check, is my machine still in a good condition? So maybe it's not a problem based on the process, but a problem of my machine that I produce bad parts. And of course, spindle and tool overload protection. And finally, this all relates to digitalization. We have a full process documentation. We can get remote access to the process situation, and of course the automatic process control by our Spike KPIs, or even further sort of Spike AI. So we cover the whole range that relates to digitalization in machining. Now let's move on to some process analysis. What we see here is a result of a milling operation where we had chatter marks at the beginning, which you can see here in area 1. Now, goal was to reduce the chatter of the tool by just adjusting either the RPM rate or the feed rate of our tool. So what we did in this specific case is we increased and decreased the RPM in 5% steps with the potentiometer of the machine. And now, as you can see, with an increase of RPM, which is in area 2, we also have a reduction of the amplitude and bending moment, and at the same time a very straight and clean line in our Spike Polar. Then we reduced the RPM rate again, and you can see with a low RPM we again have very high amplitude. You can also see it in the Spike Polar that we have a wide variety of measuring points in the Spike Polar, and back to the medium RPM rate we had at the beginning, we also have the similar amplitude and bending moment. So by just looking at our forces now, we are able to say, all right, with a higher RPM rate, you'll have less chatter marks on your surface because we have the most evenly distributed forces, which can be seen both in the bending moment as well as in the Spike Polar. So we are able to identify the ideal parameters. In this case, it was the high RPM rate, by just looking at amplitudes of bending moment and the Spike Polar. Now, what we've done quite easily was generated measuring data. We went to customer's machine, run their process, and generated measuring data. Then we try to interpret these data or evaluate these data, pre-processing of the data, and maybe also try to define some KPIs. And the next step, of course, will be an automatic control via machine connection. So there are a huge variety of things that can be thought of. And as you can see from this list, with our feed rate or RPM problem, there are just a few that fit to your needs. This might be adaptive feed control, a quality report maybe, or an app alert or red traffic light. All the others does not fit to your demands. And this is one message I'll give you today, which is really important. The type and scope of automatic control depends on individual requirements from you as the customer. So you need to tell us what needs to be monitored. So we are able to, I say, read like the process properly, but we are not able to read your mind. So you need to tell us what you need. And then we are able to get onto your challenge and see how we can handle this. So identify requirements and specifications. As said, what should be detected? In this case, it was chatter marks. It could also be surface, shape, position tolerance, drill offset, whatsoever. As said, this needs to be told us by you. Now, since we generated the data, we as pro-micron then are able to say, all right, how should or how could we monitor this problem? Is a single envelope curve enough, or do we need to implement the spike polar as well? Or do we even need spike KPIs just to cover your demand perfectly? This will be done by us, but in strong cooperation with you, so that we can perfectly fit our solution to your demands. Now, we told you how we could monitor. Next action will be back to you. What should be the reaction? Do you need a machine stop, a quality report? Do we need the process to stop, or whatsoever? Again, you need to tell us what you want to the machine to react like. And then again, we can tell you how our solution would look like. And at this point, we'll also need to get the machine and the control manufacturer get into the project, because you can imagine if we are now like increasing or decreasing the feed rate or stop the machine, there might be the issue that the machine operator says, hey, wait, why are you handling my machine and why is it not me handling the control system of the machine any longer? So this is a question of insurance, why at this point also the machine and the control manufacturer needs to be involved. Good. Before I go on with the use case of hard turning, are there any questions so far? Good. Then I'll move on to the specific use case. So I already showed you our 4 steps in the slides before, but now I'd like to specify the 4 steps or our 4-step plan to cost reduction. Step 1 is the process identification. Which processes are relevant and what are the low-hanging fruits? We've heard this before. Step 2, first analysis, process and data evaluation. Complexity of the process, which shoulder, which machine, are there any competitors on the market that could provide a similar solution for a better price? Might also be the case. And of course, a test day with Spike to gather data. Step 3, verification, long-term diagnosis. Either with a Spike mobile and a Connect Advanced system with force-based trigger or M command trigger to record long-term data. You'll see later on why it's absolutely necessary to gather data over a longer time of period. And finally, the full implementation and machine integration as a permanent installation. either as the Spike Mobile solution as said, or Spike in Spindle if you buy new machines as well. So we'll go through these 4 steps on the specific example of a compressor wheel of a turbocharger. So let's start with step 1, process identification. Again, which processes are relevant? What are the low-hanging fruits? As said, low-hanging fruit means they are easy to monitor, but they also provide a high saving potential. We have come up with a question sheet which asks you for the rejection rate compared to the product value, the process stability compared to the quantity of parts, and the tool lifetime compared to the tool costs. And we provide a matrix straight away which labels how this specific question will affect your low-hanging fruit potential of the process. So you can see right there, process 1, we have a low rejection rate, low product value, so 4 points here. In this case, we are somewhere in the area here where we have 2 points, and again, we have a high tool lifetime and low tool costs, so we come up with 10 points, which is quite much. So this process might not to be monitored, or there might be no need to monitor this at beginning. So let's focus on another process, like this one. We have a high rejection rate and a high product value. We also are in the middle area here, and we have either a unsteady tool life and medium tool costs, or high tool costs and medium tool lifetime. So we only come up with 3 points in this case. So this will be the process we'll have a closer look at in the first step. So ask us for the low-hanging fruits question sheet, and you can analyze or label your own processes today or maybe tomorrow, so you can start straight away with step 1. Now, since we identified the process which is a low-hanging fruit, which might be good to have a closer look at, we are now able to move on to step 2. Process analysis of the measuring data. So process data evaluation, the complexity is what we look at now. So the goal is we need to find a correlation between the dimensional accuracy of the part and the spike force level. So this is the outline shape of the area around here. And special interest lays on diameter 11 plus minus 0.05 mil. We ran the process, and what we saw was quite interesting. Component 1 was sort of the preset part. We had an actual dimension of 10.54 mil, and we had quite high forces in this specific area where we need our exact diameter. Components 2 and 3 are just within our tolerance with 11.0021 and 11.0006. And we have nearly equal forces in this area of interest. Now with component 4 and 5, the insert had a manipulated cutting edge, so we chipped off less material, which let the diameter increase to 11.10 or 11.11 respectively, and we had lower forces since we cut off less material. And step 2 of the process analysis will be the holder, not just the measuring data. There's a wide range of holder we can offer for our first trial. In this case, we chose a CAP to C4 adapter in sensitivity B. So sensitivity means how sensitive reacts this specific tool holder to the forces. And what we saw earlier were filtered data. And now if we look at the raw data, we see the noise to force level is not quite good. So there's the force is too low compared to the noise of our sensor system to differentiate from the noise ratio. So for the monitoring process, we'll now move on with a sensitivity A holder. So the outline shape, everything is the same, but the sensitivity increased from B to A. So we are now able to detect even smaller forces. Since we told the customer, all right, we are able to monitor your problem, we saw that the data relate directly to the actual diameter you get, and also we can provide the perfect tool holder. Let's look at the amortization. So how long will it take from your invest until you start saving money? And what we came up is with, due to reduction of tool costs, reduction of machine costs, of tool testing costs, of production error costs, and mainly due to reduction of quality related costs, we can save you almost €500,000 per year. All right, so now we are done with step 2. We analyzed the data. We saw, all right, data complexity is okay. We can monitor this. Holder is okay. Competitors are none that can monitor it this good. So amortization is done. Let's move on to step 3, long-term diagnosis. This means one spike system will be set up in the machine and just gathers data during the serial production. So there's no machine reaction at this step. We just capture more and more data to see if there are any fluctuations in the process or something else. So again, our part here, and now the complete measuring data. This is a new tool, and to a later state, to a tool where the cutting edge broke. And we are able to see this in area 6. With a new tool, there are quite high forces and also a quite high amplitude. This is in the area somewhere around here, where the wheel is friction steer welded to the shaft itself. So this welding area causes higher forces and a high amplitude and led to a tool breakage. So due to the long-term diagnosis, we were able to say, all right, we are not only able to see if you are within your limits or if you are within your tolerances, we are also able to see when your tool breaks, so you can now automatically change your tool. Now, since we came up with all these, next step will be the implementation. I don't want to go too much into detail with you on this slide because there is so many information on this slide, but it just should give you a short overview that there is everything possible, but again, the level of integration depends on individual requirement of the customer. So you need to tell us how integrated the system should be. Is it enough to just give digital or analog signals back to the machine? Or do you need a combination with the NC program or the tool database whatsoever? So it is possible, but it depends on your demands. Now, an example from serial production. We've seen this before, the machinery park, where the spike systems run in all these machines. And this is a charging concept we came up with. So there are many spikes in this operation. You have a charging terminal where you can see the status of every single spike. And you have the whole range of spike systems standing in a row, just waiting for the next operation. Now, let's have a quick look on how a long-term diagnosis could look like in this case, wear detection. So we are manufacturing just straight lines to simulate the tool wear. And you can see here the measuring data, the live data on top, spike polar on the right side. And down here you can see how the force rate behaves over time. So after every single step we mill, there's one measuring point analyzing the average bending moment within these green lines here. Now over time, you can see that the force increases, and now you are able to set limits, a yellow and a red limit, and this limit can give you a feedback in the first step just as a app alert or even a red light signal, or if you want to have it integrated with the machine at this step, could also stop the machine. But for long-term diagnosis, there's no need to have a complete integration in the machine at this step. It's just to record data and to give you a outlook how your process automation will look like later on. So let's just recap the 4 steps. Step 1, identification. Again, start off with the low-hanging fruits question sheet. So feel free to ask us for this sheet. We'll provide this for you so you can start analyzing your own process if it's interesting to go on the next steps with Spike here. Then the first analysis, we'll come over to your site or send you the test equipment so we can gather the first measuring data. The verification, long-term diagnosis, and the fourth step, the implementation and machine integration. Why is it that we came up with this 4-step plan to the complete monitoring solution for your needs? It's quite easy. If we see in step 1, all right, we identified one process that might be interesting, but with the first analysis of the data, we see it's not possible or very hard to monitor this step. We are able to get 1 step back. We can do the same thing after step 3 and go 1 step back to have a closer look again. So after every single step, we can come together, discuss what we've seen by now, what the next steps will look like, and together decide, should we go on or should we stop or go 1 step back at this point. That's why we came up with this 4-step plan to reduce the costs in your serial production. Then I'll show you some saving potentials in serial production. In this case, a thread mill. So because of confidential reasons, we are not allowed to show you all the data, but you can see the possible turnover is quite high, and at the same time they have a quite high Q&A costs every year. We came up with 2 possible approaches for this customer. Approach 1 is the increase of production. So we told them your quality costs make up quite a high amount. That's because your quality check on the machine takes longer than the process itself. So with the Spike, we were able to monitor this process in line, and in line give him a quality-related data, so he is able to see straight away if his part is good or not. So he can get rid of the Q&A costs and time. So within 15 months, he'll amortize his invest by only having a inline quality check. Now, the second approach was, since we now get rid of the quality checks, we are able to produce more parts within every shift. And since we are running 3 shifts by now, you will be able to go back to just 2 shift work, get rid of the 3rd shift, and still have the same amount of parts produced every year. And if you are doing this, your invest will even return in just 10 months. Another example from a deburring operation. Again, you can see quite high amount of parts which are manufactured, also many machines that are producing these parts. And again, it's the quality costs that led this customer to struggle with this process, because he had high quality costs and also much time spent on quality checks. So we went into the amortization, looked at the potential, and we came up with a saving potential of nearly 1.7 million euro every year. Now, the invest was around about 1.5 million on this serial production or monitoring solution, so you can calculate it for yourself. So again, he had an invest of about 1.5 million, and within 1 year he was able to save nearly 1.7 million. So under 12 months for him to amortize this project. Now, what do our customers say that uses Spike in serial production or serial production related customers? Company Bosch. With Spike and its ability to detect even the finest bending moments in the series process with power grip, we can ensure the high and increasing quality requirements in surface treatment that our customers expect from us in 24/7 production. The proactive and efficient project planning with the involved machine and tool suppliers by the pro-micron team should also be emphasized. Stefan Wagner, head of process development machining at Bosch, said this about our monitoring solution. Ceratizid, the Spike sensory tool holders are the ideal complement system to our in-house 4.0 solution, such as the ToolScope process monitoring system. Even in very fine machining process with the smallest tool and low mechanical pressure, detailed data is collected, enabling even more comprehensive and precise process monitoring. As a tool manufacturer, we have also successfully used pro-micron Sensorics tool holders in our own tool production as well as in development. Spike enabled us not only to collect mechanical data, but also to measure the temperature in the tool core during operation. Based on this data, we were able to further optimize the quality of our tools. Told by Gerhard Beilom, CEO of Ceratizid Deutschland GmbH. And finally, Heule, the product Spike Mobile of the company pro-micron, has been successfully integrated on several serial productions in the meantime, and the rollout is running on all machines. From the very good experiences from this project, I recommend this solution to customers with the need of detecting the sporadic error. It increases our process capability to a level that has not been reached before. René Kehl, Key Account Manager of Heule Werkzeug AG. So you can see the customers that are using our system in serious production or are directly related to our monitoring solutions, they are quite satisfied with the solution we offer. Now, at this point, I'll come to an end. So this was the fourth and first to the last webinar, cost saving in line production with Spike from week 25 to week 26. We'll have the use cases and FAQs. So we were gathering the FAQs and the use cases from the market and assembled a webinar to address your questions directly. And after we finished all our webinars, from the 1st to the 3rd July, we'll have an online event along the machining value chain, a chain which is called Digital Machining Marketplace, DMAP. There are companies like Ceratizid, PTW Darmstadt, pro-micron, and others, which will have webinars and online sessions during this DMAP. And I'd like to invite all of you to join this DMAP as well. So, do you have any questions until this point? Thank you again very much for your attention today. As said, the DMAP will take place from the 1st to 3rd July 2020, and here are all the exhibitors that will hold the DMAP together with us. So WZL of the University in Aachen, ISF, as said, University Darmstadt, IHK in Schwaben, Ölheld, Ceratizid, Regofix, Stama, Hermes for our grinding partners, Haas, and we as pro-micron. So I would be very happy to see most of all of you, or all of you, in this sessions as well. And thank you very much for your attention.